There are two ways to treat kidney stones: treatment A and treatment B. According to one hospital's actual records, treatment A worked better for patients with small stones and also for patients with large stones. Since A won in both groups, there seems to be no reason to hesitate. Yet when you combine the same patients and recompute the totals, treatment B's success rate comes out higher, as if by some trick. Same patients, same numbers, yet the conclusion flips to the exact opposite. The calculation isn't wrong and there's no trick anywhere. The side that won every part loses overall. The trap that fools people most often in statistics is exactly this: Simpson's paradox. What's frightening is that the data didn't lie. The data was honest. It's just that, depending on how you group it, the direction of the truth flips entirely. The first trap needs no grand data set. A sheet of paper and 2 sales reps will do. Here are GA's and NA's success rates over 2 quarters. The success rate is the number of successes divided by the number of attempts. In the recession-hit first quarter, GA was at 60% and NA at 50%. The winner is GA. In the booming second quarter too, GA was at 90% and NA at 80%. The winner is GA again. GA wins in both quarters. Yet when you add up the whole year, GA is 69 out of 110, and NA is 85 out of 110. GA's full year is about 62.7%. NA is about 77.3%. Overall, NA is far ahead. Rep GA, who won both quarters, loses when you combine them. There's no mistake in the math. The side that wins in every part can lose overall. If these feel like rigged numbers, here's a real case. Major League Baseball's Jeter and Justice. Justice has the higher batting average in both seasons. Yet combined, Jeter comes out higher. Exactly like the sales reps. The hint is a number we slipped past: how many times they tried. It's hidden right there in the denominator. In 1973, the graduate admissions results at the prestigious UC Berkeley sent shockwaves across America. Among men, about 44% of 8,442 got in. Among women, only about 35% of 4,321. 10,000 applicants, a 9 percentage point gap. To anyone, it looked like gender discrimination against women. A worried dean handed the analysis to a statistician, and the picture, split by department, was entirely different. Look at the 6 departments with the most applicants one by one, and the landscape of admission rates changes completely. In 4 of the 6, A, B, D, and F, women actually had the higher admission rate. In 1975, Berkeley published in Science. Not discrimination, but a slight bias in favor of women. So where does the overall 9 percentage points come from? The secret is that men and women applied to different departments. Men flocked to the easy A and B, while far more women took on the fierce C and E. The bar itself wasn't unfair to women. Women just clustered at the harder doors, which dragged down only their overall average. Berkeley was about reputation. This time, lives were on the line. Treatment A is open surgery. B is a minimally invasive procedure. We split the patients by stone size. For small stones, A is 81 divided by 87, 93%, versus B at 87%, so A wins. For large stones too, A is 73% and B is 69%, so A wins. A wins in both. Yet add them all together and it reverses. Treatment A overall is 273 out of 350, about 78%. Treatment B overall is 289 out of 350, about 82.6%. Combined, B wins. In the 2 groups on the left, the blue A is higher than the orange B, but on the far right, in the overall, the orange B overtakes A. Doctors mainly used A on the dangerous large stones and B on the safe small stones. The difficulty of the patients each took on was different from the start. If you look only at the overall numbers and recommend B, you actually miss the better A. Lump statistics nearly steered a life or death decision the wrong way. Now it's time to crack the secret. The salespeople, the baseball players, and the kidney stones all hid the same culprit. The key is the number we keep skipping over, the denominator. Combining 60% and 90% doesn't make 75%. Rep GA ran 100 attempts at the low 60%, so his total drops to 62.7%, Rep Na ran 100 attempts at the high 80%, so hers rises to 77.3%. It wasn't a difference in skill. It was when each one made the most attempts that set the overall average. Picture a seesaw. Hang the success rates at the two ends and add weights for the number of attempts. The fulcrum is pulled toward the heavier weight. Rep Ga's 100 attempt weight hangs at the low 60% spot, and Rep Na's hangs at the high 80% spot, so the total flips. It's the same with baseball. Jeter ran 582 at-bats in his good year in rows, and with the stones, A mostly took the hard large stones while B took the easy small ones. On the left, A took more large stones and B more small stones. On the right, the yellow star for A is pulled toward 73% and B toward 87%. A third factor that is distributed differently across the groups and also affects the outcome is called a lurking variable. For the salespeople it was the quarter, for Berkeley the department applied to, for the stones the size, and for baseball which year it was. When the lurking variable isn't mixed evenly but skews to one side, Simpson's paradox rears its head. Seen as a formula, the overall ratio isn't a simple average but an average weighted by the denominator, and the weight W comes from the number of attempts. Suppose one side comes out ahead in both Group 1 and Group 2. Yet when the weights differ, the inequality flips once you combine them. This single line is the whole of Simpson's paradox. Plugging in, treatment A has a large stone weight of 0.751, giving 78%. Treatment B has a small stone weight of 0.771, giving 82.6%. A 1 in both, yet overall B wins. Now we'll switch the paradox on and off by hand. Let's return to the two reps from Chapter 1. We keep the quarterly success rates fixed. Rep GA is at 60 and 90, Rep Na at 50 and 80, so GA is on top in either quarter. Total attempts per person stays fixed at 110. The only thing we change is how lopsidedly the attempts pile up across the two quarters. Look at the two ends of the figure. On the left, attempts are split fairly. On the right, they're skewed. As on the left, when both try 55 each, half and half, the overall winner is GA2 75% to 65%. On the right, GA piles 100 attempts into the hard Q1, while Na piles 100 into the easy Q2. The quarter-by-quarter ranking stays the same, yet the overall flips. GA at 62.7%, Na at 77.3%, so Na wins. If you keep the success rates fixed and only ramp up the skew in attempts, at some point the overall winner crosses over from GA to Na. The culprit was not skill, but which side the attempts piled onto. This time let's see in a single picture that the same trap also hides in a smooth run of numbers. Common sense says the more you exercise, the lower your cholesterol should go. But if you plot all the points together, it looks like it goes up instead. The culprit is age again. The older you are, the more you exercise and the naturally higher your cholesterol becomes. Within the same age group, the more you exercise, the lower your cholesterol. That's the real story. Ignore the age groups and combine, and it flips the other way. The colored clusters are the 20s, 40s, and 60s. The lines within each cluster all point down, and only the overall yellow dotted line points up. The slopes match too. 20s minus 4.65. 40s minus 6.60, 60s minus 9.30. All three are negative. But the combined slope is plus 7.43. Three negatives flipped into one positive. Simpson's paradox seen as a picture. Now we stand before the scariest question. When the split conclusion and the combined conclusion differ, which one should you believe? Surprisingly, you can't settle it by the numbers alone. The criterion is causation. First, the kidney stones. The size of the stone governs both the choice of treatment and its success. When a common cause is involved, you must match for size before comparing to be fair. Then treatment A is the right answer. Second, Berkeley. Here the department sits right in the middle of the road between sex and admission. If the question is whether the review itself was fair, you must compare within the same department. The overall gap arose because more women chose the narrower doors with admission rates in the 30% range. Third, when a mediator sits right in the middle of the road to the outcome, you should instead combine. Suppose a drug prevents disease by lowering blood pressure. Blood pressure, too, sits in the middle of the road. If the question is the drug's total effect, you must not split by blood pressure. It blocks the very pathway. That is why the story that settles the answer can only be brought in from outside the table. Combining means flattening one dimension, pressing it flat and erasing it. Colin Blythe pointed out that this paradox is a counterexample that breaks the sure thing principle. Data does not lie, but data alone cannot tell the whole truth. With no hard formulas, just a handful of small numbers, we've traced the most famous trap in all of statistics. The sales reps, 2 baseball players, Berkeley, kidney stones, exercise, and cholesterol. 5 stages in all. What broke wasn't the arithmetic. It was the belief that if something holds in the parts, it must hold for the whole. The lesson in one line. An average that lumps several groups into one can flip each group's truth into its exact opposite. Whenever you meet a big number like an overall average or a nationwide statistic, ask back. Could this be lumping together groups that differ? Could there be a group hidden inside that points in the exact opposite direction? An ad's average satisfaction score, a news report's income growth rate by income bracket, a company's combined results across departments. For over 100 years, the weapon Simpson's paradox used to fool us was our own complacency, the assumption that combining things will, of course, behave as expected. If you found today's video helpful, please subscribe and like. See you in the next video.